Okay, welcome back, and let's just have a look at the solution to question 2, which hopefully you've already done. The limit as n tends to infinity of n times sine n. I'm going to use L'Hopital's rule, so I write this in terms of x because I want to think of it as a functional limit. So it's the limit as x tends to infinity of x times sine pi on x. This is the indeterminate form, infinity times 0, and I've got a choice. I can put one of them or either of them on the bottom. And I choose it so that I get an easy differentiation. So what I did was I put the x on the bottom and made it 1 on x. So both of these terms now are turning to 0 over 0, so I quote that I'm using L'Hopital's rule. I differentiate the sine pi on x, and I get cos pi on x times pi, and then the derivative of the 1 over x. And of course that very neatly cancels out straight away with the derivative of the 1 of the x on the bottom, and it just leaves me with this limit here. I use the continuity of cos, and the answer turns out to be pi. Okay, this limit can also be written in an interesting geometrical way, so I wanted to show you that as well. And what I can do is I can think about the unit circle here. So here's a unit circle, radius 1. And I'm going to put a regular n-gon. So it's an n-sided figure, an n-sided polygon inside the circle. I've drawn 2 bits of it here, but it keeps going all the way around, and it has n sides. So the angle around the whole circle is 2 pi, and I've got n sides. So this angle here, that angle is 2 pi divided by n. And I'm going to try and calculate the perimeter of the polygon. So I need to know what this total length here is, the length of a side. And the way I'm going to do it is I'm going to put this right angled triangle in here, where this angle is half of the 2 pi. So that's the angle pi on n, and the radius of the circle is 1. So you can see that this distance in here, half of the side length, is actually sine pi on n. So that means that the side length is 2 times sine pi on n, and the perimeter, if you like, of the n-gon, I write it as Pn, it's the total perimeter of the n-gon, is going to be n, well, it has n sides, so it's n times s, which is 2n sine pi on n. So if you look at this geometrically, you can see that as I chop the circle up into more and more bits, I have a larger and larger n-gon fitting inside. The actual perimeter of the n-gon will always be smaller than the circumference of the circle, but it will tend to the circumference of a circle as a limit. So what I'm expecting is that the limit as n tends to infinity of the perimeter of the n-gon, where you can see here that it's the limit as n tends to infinity of 2n sine pi on n, and that's the limit that we've just evaluated, and it's actually equal to 2 pi, which is 2 pi, if you like, times 1, because the radius of the circle is 1. And so the limit that we've shown shows that the limit of the perimeter of the n-gon actually tends to pi. This process of putting an n-gon inside a circle, and also you can do the same thing with an n-gon that actually sits just outside the circle, was an argument that was used by Archimedes to actually get some limits on pi. And he figured out that pi was between 3 and 1/7 and 3 and 10 on 71 by using an argument exactly like this. And if you're interested to play around with it, I have a little GeoGebra applet which is available on the website, and it just enables you to look at the perimeter. So here n is equal to 3. I've got an equilateral triangle inside the circle, and the perimeter of that actually is 5.19. And also this applet is calculating the area as well. And so what you can do is you can increase the size of n. So now I've got a square. The perimeter of the square is 5.65. I can go to a pentagon, I can go to a hexagon, I can go to a septagon, and so on. And you can see that as n increases, the perimeter of the n-gon gets closer and closer to the circumference of the circle. So as I increase n here, I'm expecting the total perimeter of the n-gon to be the circumference of the circle. So that should be tending to 2 pi. And the area is pi r squared and should be tending to pi. So you can see as I do this, I'm expecting the perimeter to be 2 pi, which is about 6.28. I'm expecting the area to be pi r squared. R is 1, so that's 3.14159. Okay, so you can actually have a play around with that, and you can actually increase the value quite significantly here. So that's a geometrical interpretation of the limit that you've just evaluated using L'Hopital's rule. So now we should have a look at question 2, part B. So I've written out the full solution for that. The main point I wanted to make here was that this was an indeterminate form. It's infinity minus infinity. So whatever you do, don't write infinity minus infinity equals 0. You've got to figure out, there's two things that are getting big, and you need to figure out what the relationship between them is, and you need to change the form of it. This is pretty standard argument by now. You've seen this quite a bit. You've got, a square root minus another square root. And the obvious thing to do is to use the difference of two squares. So you multiply by the conjugate. We're using this pattern, a squared minus b squared is a plus b times a minus b. So when you do this product up here, you shouldn't waste time multiplying it all out. You should just say, look, it's a minus b times a plus b. So it's a squared minus b squared. And each term here is a square root, so it just disappears. So you just get e to the 2x plus x minus e to the 2x minus e to the x. So you actually end up with a plus there. And you end up with this expression down the bottom. Now, when you look at the top, there's an e to the 2x minus an e to the 2x. That cancels. And so you're left with 2 times e to the x. Now, I can see straight away that what I'm going to have to do, because that's tending to infinity, is divide the top and bottom by e to the x. So I don't make extra work for myself. I've skipped a couple of steps here, but I'd hope that you can do this after a while. You'd see the top is 2 times e to the x. It's tending to infinity, so you divide by e to the x, and then you look at the bottom here and you say, well, I'm dividing by e to the x each term. You put it inside the square root, and the e to the x becomes an e to the 2x. And so I've written it down straight away. I've just written what I've got inside here is divided by e to the 2x. So I get a 1 here, and a 1 over e to the x, and a 1 over e to the minus x. 1 over e to the x here. 1 minus e to the 1 minus 1 over e to the x. So I'm left with a 2 on the top. When I evaluate the limit on the bottom, I'm using the continuity of the square root function. The limit of the square root is equal to the square root of the limit, and I use the fact that e to the x tends to infinity as x tends to 0, so 1 over it tends to 0, so I end up with a limit of 1. Okay. So now I'd like to move straight on to having a look at question 3, and this is dealing with series. And we need to use the comparison test. So we're being asked to tell whether this series, summing up these terms, whether that's convergent or divergent. And we're going to have to use the comparison test. Here it is. We've got a series, sum an, another series, sum bn, and they're all positive. They're all positive term series. If the nth term of the A series is smaller than the nth term of the B series for all n, In fact, it suffices if it's true for all n greater than some fixed n. And Bn is a convergent series, then if you like, the AN series is dominated, it's underneath a convergent Bn series, and it also converges. And alternatively, if the series Bn diverges so that the sum of this doesn't tend to a limit, and for our AN each term is bigger than the term, all the terms of the divergent series, then the series AN will diverge because it's sitting, if you like, on top of a divergent series. And so as it says here, most of the time when we use the comparison test in Calculus 2, we make a comparison with other harmonic p-series or the geometric series. So let's go back and have a look at this example. What we want to do is we want to look at the size of the nth term of this, and we want to get a rough idea how big it is. So we're just doing order of magnitude calculations here. So we say root n minus 1 on n squared plus 1. What does it look like approximately if n is really large? Now the top just looks like root n. You can forget about the minus 1, that doesn't make much difference. And on the bottom it just looks like n squared. And so there's an n to the half on the top, an n to the 2 on the bottom. So I get n to the 3 on 2. The harmonic p-series is the sum of 1 over n to the p, and that converges, we are told in the lecture notes, when p is bigger than 1. So my p here is bigger than 1, it's 3 over 2. So immediately what I do here is I say I guess that my series here, let's refer to it as sum an, if you like, to fit in with the lecture note definition, converges by comparison with the convergent harmonic p-series for n equal to 3 on 2. So what I've got to do is I've got to show somehow, so I need to show that my AN terms are smaller than the terms of the convergent series that I'm comparing it with. So I need to show that the square root of n minus 1 over n squared plus 1 is smaller than, now I'm going to leave a gap in here, I'm going to have a series of arguments in here, but I need to know what I'm comparing it with, and what I'm comparing it with is the harmonic p-series 1 over n to the 3 on 2. But I don't necessarily have to compare it with 1 over n to the 3 on 2. I can, if I wish, introduce a factor of k here. This is a convergent series, and if I multiply it by k, I don't change the fact that it's a convergent series. So that allows me some flexibility in the way I set up the inequalities. So I just like to sort of motivate what's happening here. This term an, if you like, of our series, we want to show that they're all smaller than this convergent harmonic p-series. And I just want to show you the applet that you've seen in lectures. I've set this up. So this is available to you. You can choose a harmonic series with p equal to 1.5, which is 3 on 2. This is the convergent series that we're doing the comparison with, and you can see that it converges to a limit. The applet is telling you that limit is around 2.5. So what we've got is our series is underneath here, and every term is no bigger than the terms of this. So here's the first term, we add in the second, we add in the third, and so on, and we approach this limit. With our other series that's sitting underneath the convergent series, we're starting off somewhere down here, then we add something, now maybe not as much as this, but we still add, and then we add a bit more to get the third term of the sum, and we go up a little bit more. It's a series of positive terms, so we can't wander down, we have to keep going up. But we can't go up forever, And in fact, we can see straight away that we never get above the sum for the convergent series, because every term of R1 is smaller than that. So R series has to keep going up and up and up as we add more and more positive terms, but it can't keep going up forever. It can't go above this limit, and therefore it must approach a limit. That's basically the idea of the comparison test in this case. So if we go back, well, the main thing we've got to do here is we've got to get this set of inequalities. And people often have trouble here because they need to do something different to the top and the bottom. So I just want to give you a little way of remembering what to do here. Let's say I've got a fraction. I've got something on the top, the first thing that I've got on the top, and I've got the first thing that I've got on the bottom, and I know what the direction is. I want to be less than. Well, if I'm not going to touch the bottom, say, right, if I want to write another fraction, clearly here I have to replace the top by something else, T2, so that T1 is less than T2. In other words, I need to make sure that the top gets bigger. So what's happening with the size of the terms on the top is it's following the inequality that you've got. But if I then say, okay, I want this to be less than, and I leave the top the same, let's say I'm not going to change the top, what do I need to do to the bottom? Well, what I need to do to the bottom, instead of making it bigger, I need to make it smaller. So I need to replace what's originally on the bottom, the first term on the bottom, B1, by a B2, where B2 is actually smaller than B1, or that B1 is actually bigger than B2. Now the reason for this is quite simply that the function 1 over x, if you graph it, is a decreasing function here. So if you choose a B1 which is bigger than B2, so in other words you replace what's on the bottom by something that's smaller, you can see immediately that that means that 1 over B1 is actually smaller than 1 over B2, because 1 over x is a decreasing function. And so a way of summarising that, if you like, is that B1 has to be bigger than B2, i.e. the bottom gets smaller. So if you want to keep getting these inequalities nice and simple, you want to be less than, the top has to follow the same rule as this. So when I put a fraction in here, I'm going to have to make sure that whatever I put here is actually bigger than this, but this has to be smaller. So the bottom just goes in the opposite direction. And the motivation is to get something that looks like this. Now if I didn't have the -1 and the 1, I would get to this form directly. So I'm trying to find a way to get rid of the -1 and the 1. So on the top I want it to get bigger. Well, I can get rid of the -1 straight away just by replacing it by √n. That's really easy. And then I need to make the bottom go in the opposite direction to the inequality. So I need to make it smaller, and I can do that just by taking the 1 off. And so this works directly, and this is just equal to 1 over n to the 3 on 2. In other words, in this case, I didn't need a different sort of k. I've got k equals 1. And that's the inequality that I need to prove. So then I can say by the comparison test, the sum from n equals 2 to infinity of √n minus 1 on n squared plus 1 converges. So question 3 part B, which we move on to now, operates in a very similar way. So let's just think through it very quickly. First of all, I want to see what the size of the nth term is. For very large n, it's going to look like n on the top. On the bottom, the dominant term is n squared, so this is going to be approximately n on n squared, which is 1 on n. Now the sum of 1 on n is the harmonic series with p equal to 1, and I know that it diverges. So I think that the next thing that I write here is that I'm going to guess that the series diverges. Then I'll follow my standard format. Okay, if I want to show that it diverges, then what I need to do is I need to make sure that I can show somehow that my term, the nth term of my series, is going to be bigger than, okay, leave a gap here. What am I going to be comparing it with? I'm going to be comparing it with, I want it to be bigger than 1 over n. Oh, well, I can afford to multiply that by k. Sum 1 over n diverges. If I multiply it by 2, it still diverges, so I can afford to have a k there. So then I say to myself, okay, I want this to look like this in form. If I didn't have the n and the minus 1, I would be there directly. So that tells me that what I've got to do is somehow do something with these. These are getting in the way of me making this look like this. That's why it's important you write this down so you know what you're aiming for, because you're going to think about how to change this so that you get that. Okay? And we also know the direction. We will need to be bigger than our divergence series, so the comparison test will give us divergence. Okay, well, if we want to do that, the top will follow this inequality. Now, I don't have any terms on the top that are bothering me, so I'm going to leave that the same. So, now what am I going to do on the bottom? Well, this whole fraction has to be bigger than this, so I know when I'm on the bottom I need to change the inequality. So what I need to do is whatever I put here, it has to be bigger than this. Oh, well, that means I can get rid of the 1 straight away just by writing n squared plus n. Okay? So as this series of inequalities continues, I'm remembering that I would need to make the top smaller with the inequality. I need to make the bottom flip the other way. It needs to be bigger. Now, this n is getting in the way of me sort of dividing the n and the n squared. And so this is really an algebraic trick. You've seen it before. But what I can do is I can say, okay, I'll leave the top the same. Now, I need the bottom to get bigger, and I can make it bigger by replacing n by n squared. And the reason I do that is so that the whole thing will cancel nicely, because I can see now that this is really just equal to n over 2n squared, and that is equal to 1 over 2n. And so if you like, I've achieved what I wanted to, but with k equal to a half. Okay, and therefore I can say by the comparison test, the sum n equals 1 to infinity of n over n squared plus n minus 1 diverges. Now, the final video in this consultation is to some extent optional. I want to talk about the divergence test because people often misapply that, and then I'm going to try to motivate, show you a couple of other interesting things which aren't essential, but I'm hoping that you'll find them interesting and enlightening.